Hello, I'm Aksel Veak, an undergraduate research assistant at Purdue's Electric Propulsion and Plasma Lab, and I'm here with my colleague and graduate student Nick Babusis to give an introduction to the theory and experimental setup of coherent microwave scattering. What is coherent microwave scattering? Coherent microwave scattering, or CMS for short, is a new way of determining the properties of a plasma that our lab has been developing. Why is this important? Well, plasma is actually the most abundant state of matter in the universe and is used across a wide range of applications, like spark plugs, neon lights, and even electric thrusters for spacecraft. When you are working with a plasma, there are typically a few things you want to measure to tell how that plasma will behave. The most important is the electron density, or literally how many free electrons there are per cubic centimeter of plasma. The higher the electron density of a plasma, the more conductive, bright, and energetic it will be. There are many ways to measure the electron density of a plasma, such as conducting current through it to measure its resistance, firing a laser at it to measure its optical properties, or analyzing the spectrum of light that it gives off. All of these techniques have their pros and cons, but they are typically limited to a certain range of electron densities. CMS, on the other hand, is useful because it works over a very wide range of densities, from around 100 million to 1 quintillion electrons in its detection volume. To use CMS, first we need to start with our plasma. CMS is particularly useful for plasmas that are too thin for other diagnostic tools to be practical, but also has to be long enough for the plasma to be a similar length to the microwaves being used. This plasma can be generated in many different ways, with our method of choice being powerful focused laser pulses. This process is usually done inside a low-pressure chamber so we can control the type and density of gas the plasma we are generating is created from. Looking at a view rotated 90 degrees, we can see down the length of our plasma, and where both a transmitting and receiving horn antenna are placed, usually, in our case, oriented perpendicular to each other. Using the transmitting antenna, we shoot microwaves at the plasma. This is where things get interesting. As you may already know, microwaves are a form of electromagnetic radiation, meaning that they contain an oscillating electric and magnetic field component. The electric component in particular is important, because when electrons inside the plasma feel this oscillating electric field from the microwaves, they begin to migrate back and forth between the ends of the plasma filament. As a side note, ions in the plasma will also feel this force, but they aren't nearly as much affected due to their much higher mass. Because an accelerating charge generates electromagnetic radiation of its own, each one of the oscillating electrons will radiate microwaves back into the environment, similar to how a dipole antenna works. This is a form of electromagnetic scattering. Some of the emitted microwaves are collected by the perpendicularly oriented receiving antenna and sent to a detection circuit. This circuit then can output the power of the signal and be plotted over time on a readout like an oscilloscope. The reason this method can detect such a huge range of electron densities is because the scattering of the microwaves is coherent. Because the microwaves are larger than the plasma, every point inside the plasma sees a similar electric field at any one time. This causes the microwaves radiated by all the electrons to be synchronized, so their electric fields will add up. This means that by doubling the number of electrons in the plasma, we see roughly quadruple the power being radiated away. This differs from incoherent scattering, which we see when visible light bounces off a sheet of paper. Because the paper is much larger than the wavelength of visible light, different parts of the paper experience different electric field components and are thus emitting fields with a more random orientation and phase. These can still add up, but will partially cancel each other out due to the destructive interference occurring, and leave there being a more linear relationship between the number of molecules scattering light and the power of the radiated light. The high end of electron densities that can be detected by CMS is only limited by the density at which the plasma becomes so dense that the microwaves cannot even penetrate into it. Another plasma parameter that is important for predicting how a plasma will behave is the collisional frequency, or how many times a specific type of particle will collide with the other particles in the plasma each second. For CMS, this affects the phase of the radiated microwaves by adding a kind of drag on the electrons, so they are somewhat delayed when following the incident electric field from the microwaves. The detection circuit can determine the phase shift of the scattered signal by comparing it with the signal being transmitted into the plasma. Based on the power and phase of the received signal, we can use a bunch of math to determine the electron density and collisional frequency. Now, I'll hand it over to Nick to give an overview of the CMS setup we use in the lab.
So here's what our microwave circuit looks like that we use for CMS detection. We have here a microwave generator. This generates a 11 gigahertz microwave signal that comes through this cable here to a splitter, which then splits it. One part of the signal goes through this phase shifter, which we can use to adjust the phase, the relative phase between the microwaves that we're transmitting and the microwaves that we are using to compare against the received signal. Once the phase has been shifted, it goes into here, which is a high power microwave amplifier. And then that comes through our cable into this, which is our big vacuum chamber that we use for controlling the atmosphere that we're generating the plasma in. So inside our vacuum chamber here, we have our two microwave horns. So the transmitted signal comes down through here. And inside this horn antenna, we have a tiny little wire that radiates out microwaves and bombards this central region. Here is where our laser comes in and gets focused down by this lens into a tiny point, which is high enough power that it will actually generate a plasma filament right there. So this will be irradiating the plasma filament with microwaves, and some of those scattered microwaves will be then sent into this receiving horn, which then comes out and goes back into our microwave circuit on the other side. To cover the chamber here in these microwave absorber panels, just so that we make sure that the transmitted signal is not bouncing all around and messing with our detection circuit. So the received signal then comes out through here, travels along this cable, and goes into an amplifier. So since the received signal is relatively low intensity, we need to amplify it before we can analyze it. And that goes into this device, which is our IQ mixer. So the other half of the signal coming from the generator is put into the one of these other ports here, and these two signals get essentially multiplied together, and that allows us to compare both the amplitude and phase of the reflected signal. And that comes out of these two channels, which are essentially the in phase and quadrature, which is like the out of phase component between them. And those go into these amplifiers here, and will get sent along these channels, which will be connected to an oscilloscope, where we can monitor the reflected signal over time. And that will tell us both how the electron density and the collisional frequency of the plasma is changing over time.
Thank you, Nick, for walking us through our lab CMS setup and providing extra details on its components. Now, in conclusion, CMS is a novel method that can be used for diagnosing different properties of plasma through the use of microwaves. Its unique abilities, such as its wide range of measurable electron densities, allows it to be a new useful method in the wide toolbox of plasma diagnostic techniques used in research around the globe. Thank you for watching this video. Subscribe to see more content in the future on the work being done at Purdue University's Electric Propulsion and Plasma Lab.